Okay, so this is where stuff gets like really, really, really cool. Um, we are going to be learning about how to decipher, how to understand impulse response functions, and then what the usefulness of them is when it comes to macroeconomic analysis and research. So now, while you'd think this is going to have a lot of math, and when you read this chapter in the book, you see a lot of math. Now, in this case, I'm actually not giving you any math because all you're going to have to do is look at these pictures and tell me what they mean. That's it. You don't even have to draw the pictures out. So this is like easier than probably most of the things that you've ever done in this class. And it's also really fun because we get to use like real world data and like real world applications of these models to see if the models really fit, if they really explain things the way that the creators of the model like to argue they work. Now, when it comes to looking at data, like real world data, a variable that runs over time and has one observation per time period is called a time series. And we've been looking at time series all semester long and probably didn't even realize we were doing it. Things like GDP, inflation, unemployment, consumption, investment, all those things are time series because, well, there's one value for them each time period. So if you're looking at first quarter GDP, it's just first quarter GDP. Now, if you're looking at like first quarter GDP for all 50 states in the United States, well, that's a different type of variable that we're not going to be dealing with. Time series is just like if you had all 50 states aggregated up to one value. Now, in applied macroeconomic research, we look at how these variables interact with each other. The idea is like if we get a movement in GDP, you're probably going to see some resulting movement in inflation and unemployment and all those things. And we want to see what these movements or these co-movements look like. We talked about co-movements when we learned about the real business cycle model and the way these things move in responses to shocks. Well, this is just going to be the real world application of that because these movements, these co-movements between these variables, let us test out the theoretical predictions of these business cycle models that we've been learning all semester long. Now, in statistics, we use something known as a linear regression to estimate relationships between two or more variables, going like, is our GDP and inflation correlated? And if they are correlated, by how much? But with these two and then other macroeconomic variables as well, there's an issue because they're what's known as endogenous with each other. They kind of play a role in how the other one moves. It's like a what came first, the chicken or the egg type thing, right? That's sort of a decent, like, I guess, litmus test for endogeneity is like, okay, if you can make an argument for one thing moving and then the other moves, but if you make an argument for that second thing moving and then the first thing moves, well, it's like, all right, there's like a causation problem here. Which one caused which, right? If inflation increases, well, you could see GDP falling, but if GDP increases, inflation could also rise or fall, right? If GDP and inflation rise together, well, that's a certain type of shock. If GDP and inflation move in opposite directions, that's another type of shock. We've learned both of those shocks recently. So the source of shocks really determines what variables move and how they move. Now, what's cool about macroeconomic research is we actually depend on that endogeneity. We like it. We can take advantage of it, and we can model all of these variables simultaneously in what is known as a vector autoregression model. It's basically fancy words for saying it's a linear regression that runs over time, but it's for a bunch of different variables all at once, and every variable is going to get its own equation. So if you've got like GDP and inflation, well, you'd have an equation for GDP and an equation for inflation, and they're functions of each other's lag. So current inflation would be a function of last period's inflation and last period's GDP, and the same would hold for GDP with inflation. Now, we can then, because these are estimated equations, right? So there's going to be a little bit of error or residual, right? That residual is going to be the source of shocks to these equations. So if we do something to that residual, we can impose a shock to, say, GDP or inflation, and then see how everything responds to that shock. If everything responds to that shock consistent with the economic theory that we've learned, well, we have now just tested using real-world data how the theory works. If the theory lines up, if the data shows what the theory predicts, then the theory is good. It's a good model. If the data doesn't really work all that well, doesn't line up, then, well, maybe there are some issues. Sometimes it's with the data. Sometimes it's just with the real world scenarios that we're in. Other times it's because the model itself doesn't really hold up. So just because it doesn't work doesn't mean the model doesn't work. It could just be that there's something wrong with your modeling your statistical modeling process. It could be that the monetary policy regime that we're currently in, or one that we just got out of recently, maybe didn't line up with the way that these models are predicting, the way the models are calibrated. There's all sorts of things. So it's not just like if the data doesn't fit, then it's a crap model. So when we model all these variables together, and we model them all at the same time or simultaneously, every variable gets its own equation, just like what we saw in the real business cycle or New Keynesian models. Remember, we had there's a labor demand, a labor supply, aggregate demand, aggregate supply, things like that, right? Those are all their own equation. So these statistical models become empirical representations of the theoretical models that we've been learning about for the second half of the semester. And we can impose shocks just like in the models that we learned about and see if the responses to those shocks with real-world data line up with what the models predict. But the difference here, though, is when we're looking at time series data, we're looking at dynamic responses, meaning we look at the evolution of the responses over time. And the models that we've learned, at least the way we've looked at those shocks, are only static responses. But we can look at the general behavior of the responses and see if they match. Do they increase or decrease over time? Think of it this way, right? Look at a total factor productivity shock for the real business cycle model. What does it tell you? Well, it says output increases, right? The source of the shock is in output. So that production function shifts up. Because of that, the price level falls because you get an aggregate supply shock. Aggregate supply increases. You get a drop in the real interest rate. You get an increase in employment, hours worked, or just overall employment increases. You get an increase in the wage rate because there's that labor demand shock. Firms need more labor to produce the more stuff that they can now make. And then as a response, the central bank will be increasing the money supply, which of course then leads to that reduction in the real interest rate. So let's see if all with just those signed responses, this goes up, this goes down, this goes up, this goes down, things like that. Let's look at that and see if we can get similar qualitative results. Now, in order to get these qualitative results, right, going, okay, we're looking at the data, which is a very quantitative approach, but what's the direction it's going in, right? Do these responses show an increase or a decrease? If it's an increase, well, okay, things increased. Right now, we're currently only looking at the qualitative, increase or decrease. That's it. But in order to be able to answer that, we got to get some data. So time to go get some data. Now, I did it all for you. I went to the Federal Reserve Economic Database, and I got the PCE price index, 10-year Treasury yield. This is going to be, the 10-year Treasury yield is going to be the interest rate that we're looking at. Now, I want to be fair. This isn't the explicitly stated policy rate by the Federal Reserve, but it was argued as the transmission mechanism or the variable, the interest rate through which monetary policy most likely transmitted to the real economy during the monetary policy regime following the financial crisis, which is a good chunk of the sample period that we're looking at. I've also got hours worked, real wages, the money base, and then I went to macroeconomic advisors and I got real GDP. Now, these are all at the monthly frequency from October 2008 to September of 2023. Now, the sample reflects a couple of different monetary policy regimes, two of which are unconventional. So, the reason I started in October of 2008 is to make sure that we don't have any data prior to the financial crisis of '08, because that can cause some problems that we'll probably be talking about a little bit later. But it's really just that the monetary policy regimes are different. The policy tool was different, and the policy rate was different. Prior to 2008, it was the federal funds rate. After that, the federal funds rate was basically locked at zero. They couldn't really do a whole lot with that interest rate. So they went along further out in the yield curve, and they went with the 10-year Treasury yield, and they tried to drive down long-term interest rates to flatten the yield curve. So I guess we kind of already discussed it. Long story short, short-term interest rates were too low to do anything, so they went out with the longer-term rates and tried to move those instead, which is why I've got that in the specification instead of just the federal funds rate. So now, if we're going to be responsible researchers here, the first thing that we're going to want to do is plot the data and see how it behaves. So I plot the data out, and I plot a lot of them out in natural logarithms. So real GDP, prices, the money base, real wages, and hours worked are all plotted out in natural logs. It gives us some nice statistical properties for these variables, and it makes sense to present the data as it's used in this way. So this is all the 6 variables that I've got. 5 of the 6 are expressed in natural logarithms. And this is what we got. So these 6 variables are what we use. Now, when I run the model, I get something that's called an impulse response function. And that's that whole thing I was talking about earlier. Like, I estimate each equation, I get these residuals for each equation, and then I play around with the residual, which then causes the model to respond a certain way. The way it responds is defined by the impulse response function. And it's going to show the evolution of these macro variables in response to a shock to one of those variables or one of those equations. Now, it's generally treated as a 1 standard deviation increase in that variable's equation. So if there's a shock to GDP, well, it increases the residual in the GDP equation. And we can say there's a total factor productivity shock and then see how all the other variables respond given the shock to the GDP equation. If we can isolate the shocks to each equation and not have these shocks like bleed over into the others, well, then we've identified the model. Identification of the model is like what we were talking about earlier, being able to tell the difference between 2 shocks. If you can tell the difference between a total factor productivity and a labor supply shock, well, then those shocks are identified. The model is identified. It's the same idea here. Now, I actually take this a step further, and I restrict the responses to be either positive or negative, and then I see if the variables move like they're supposed to. So if I'm like, I want a total factor productivity shock, well, I'll require that some of the variables move in the directions that are consistent with a total factor productivity shock, and then see if everything else responds accordingly. So if I got 6 variables, then I'll have 6 equations, and I can identify 6 shocks. Now, I'm not concerned with like every shock that we could possibly identify here. There's just a couple that I'm really concerned with. The first, total factor productivity. Second, labor supply. Third, monetary policy. I could go into like a government, but then I'd also have to throw like a government variable in there, and I just don't really want to have to deal with that. We're not going to worry about the government spending stuff. The monetary policy shocks, I think, are a little bit more interesting. May have something to do with the fact that I studied monetary economics in graduate school, and my dissertation is written in monetary economics. So think of it like this. With a demand shock, all right, when you look at a demand shock, demand increases, output and price move in the same direction. So if demand increases, output and price will increase. I got a pretty little picture here as proof. So demand shifts from AD1 up to AD2, and the price level increases from P1 up to P2, and output increases from Y1 up to Y2. Fairly standard stuff for any basic economics course that you take. So if I'm looking at impulse responses, I should see the same thing, right? They should be increasing. And there'd be a time series plot for output and then another one for prices, and I would just look to see, okay, does output increase? Do prices increase? Well, if I did that, let's see. Let's look at this. What are we looking at here? Well, this red thing is the impulse response function. This blue stuff around it this like little blue cloud around it, is what's known as a Bayesian credibility band. If you've taken statistics, think of it as like a confidence interval. Not exactly the same thing, but close enough. So now you're like, okay, well, did they increase or decrease? What the hell did they do? Well, let's look at 0 here, okay? So if this red line just stayed at 0 and didn't go anywhere, well, it wouldn't have done anything. But this red line increased. It's above 0. If we think about this percent deviation, it's like a, 2.25% deviation from 0. Think about it like in the steady state with the Solo model, right? You learn about the steady states. This is like a deviation from the steady state. Think of it that way. It increases above the steady state, and then it kind of tapers back down a little bit and eventually settles off at something that is permanently higher than 0. So here, output increased. You don't have to look at it and go, well, it falls, output's falling. No. Did it increase? Is it above 0? If at any single point in time it's above 0, then it increased. So let's say just on impact, right? If we look at on impact, is it above 0? The answer is yes. This point right here is greater than this point right here, so it's increased. Prices. Look at prices. Did prices increase or decrease? Well, they increased, right? They increased because on impact, right, T equals 0. When the shock hits, well, this point right here is above 0, so it's positive. Now, this is where things get a little tricky. We can say with a decent amount of certainty that we got an increase. This is a statistical test. Now, remember, with statistics, you're never going to really know for sure, right? There's never any certainty. You're never proving anything with statistics. You can prove certain qualities of a statistical estimator, but you can't prove anything with the data. You only have evidence to suggest something happened with the data. So here, we didn't prove that this data shows an increase in output and price. We just have evidence to suggest that there's an increase in output and price with some degree of statistical certainty, but not absolute certainty. That's where these little blue things come in, these little blue bands above and below the impulse response function come in. If the bottom of this band is above 0, okay, well then we can say that there's pretty decent likelihood, statistically speaking, that we had an increase in this particular variable. If, on the other hand, the top of this band is below 0, well then, decent statistical likelihood that it decreased. So I can say, with a degree of statistical confidence, that output significantly increases above 0, and that price significantly increases above 0. Now, eventually, as soon as we hit this point right here, where the lower band is now crossing that 0, that horizontal axis, these bands are now on either side of 0. Because they're on either side of 0, well, we don't really know what the hell's going on. It looks like it's still above 0, but we can't really say for sure. So we just choose not to. So at this point right here, well, we don't really know what's going on. But from 0 up until this point, it's about 15 months in. First 15 months, we're pretty certain that price is above 0. And for this entire horizon here, we're pretty certain that output is above 0. So output and price are above 0. That immediately tells you it's a demand shock. This is a demand shock of some sort. So it's fairly easy to interpret, really. You just look to see if it increased. And again, you want to look at that red curve, and you don't want to be too worried about the behavior of the curve so much. So don't go like, well, is it like increasing, like it's increased here, but then like it falls and it increases and it falls again. I just want you to look and tell me, is this red curve above or below 0? And the only way to tell that sometimes, because sometimes you don't see the 0 here, sometimes you just see these numbers. Well, if the numbers are positive, then it's above 0. If the numbers are negative, then it's below 0. So try not to think too much into it, because you don't want to be worried about the behavior. Really, there actually need to be like some statistical adjustments made to those credibility bands in order to be able to really interpret like the slope of these things or the behavior of these things over time. So just look to see if it's above or below 0. And you got to look at that vertical axis to get an idea if it's positive or negative. So we saw a demand shock. We saw an aggregate demand shock. Let's look at an aggregate supply shock this time. Let's see what that does. With an aggregate supply shock, remember, output increases and prices fall. So with a demand shock, output and price move in the same direction. With a supply shock, output and price will be moving in opposite directions. So if we look at our pretty little aggregate supply shock graph here, this is what we get. Aggregate supply increases from AS1 to AS2. The price level falls and output increases. So if we're looking at the dynamic response, we should see something where price falls and output goes up. So let's look at the dynamic responses here. Boom. Okay. Output. What's output doing? Well, output is positive. It increased. So if you just look at t equals 0, did it go up? It did. It's above 0. So think about it. Prior to the shock hitting, right, everything is moving along at 0. So output would be moving along at 0. The shock hits, boom, it just jumps up. And then here we are. So it was a flat line at 0 prior to the shock. The shock hits, it bumps up, and then it does this stuff here. So what did it do? Well, it increased. How do we know it increased? We know it increased because we look at the vertical axis. We got 1, 1.5, 2, 2.5. It's increasing, right? So this is in positive territory. This is above the horizontal or the x-axis. I guess it's really the t-axis here because it's time. But it's above the horizontal axis. So output increased. Okay, cool. Check that one off. Output increased. So we got half of our aggregate supply shock figured out. Now it's time to look at what the price level did. What did the price level do? Well, this is our horizontal axis. 0 right here. All right. It fell. The price level fell. So on impact, t equals 0, the price level, bloop, dropped. All right, and it dropped a little more than 0.5%. Its maximum response is a little over 1%. And then it appears to remain below 0 for a good chunk of the horizon up until about this point. Then we can't really say anything because, well, some of the stuff is above 0, some of it's below 0. Can't really say what happened. But overall, right, if you think of even not at what happened at t equals 0, but just the maximum response, the maximum deviation from 0. For output, it's positive. The maximum deviation is right at about this point here. And you can see it's above 0. The maximum deviation is about, 1.75% above 0. And then here the maximum deviation is a little over 1%. So output increases by about 1.75 percentage points because it's not a percent increase, it's a percentage point increase. So output increases by about 1.5 percentage points. Prices fall by about 1.1 percentage points. So output increases, prices fall. Consistent with this right here. Output increases, prices fall. Now, that's just for 2 variables. So for these 2 variables, we can look at 2 shocks, and that's it. That's all we get. Demand shock, supply shock. But if we extend it beyond 2 variables, we can look at different shocks. So let's look at the 6 variables that we were looking at earlier. Real GDP, prices, 10-year Treasury yield, hours worked, real wages, and the monetary base. And I'm going to be testing out all these responses to a total factor productivity shock, labor supply shock, and a monetary policy shock. Total factor productivity shock is going to originate in real GDP. Now, the money supply shock is going to be originating in the money base because, well, it's going to be originating in that equation because the money supply is increasing. The central bank is increasing the money supply. Therefore, the money base is going to be increasing because remember, the money base is what actually gets affected in response to a monetary policy shock. And then what we're going to do is we're going to look at these shocks. We're going to get total factor productivity, labor supply, and monetary policy shocks, and then see how they compare to the real business cycle and new Keynesian models. So we'll start with the total factor productivity shock. Now remember, in either the RBC or new Keynesian model, these are the signs of the responses that we get. Output increases, prices fall, the real interest rate drops, the money supply increases, and labor and wages, the real wage, both increase. So to refresh our memory, though, let's just go look at the graph. So I got the graph drawn from the RBC chapter where I didn't have the IS and LM stuff. So really, you're not seeing what happened with the money supply or the real interest rate. But for this shock, we're not so concerned about the real interest rate or money supply. It's more what happened to labor, what happened to wages, what happens to output, what happens to price. And here we can see prices fall, output increases, labor increases, wages increase. So if the model is worth its weight in like anything at all, you're probably going to see qualitative responses that are similar to what this model should predict. And this is what we get. So what are we looking at here? Well, we're looking at the responses of all of those 6 variables that I had presented to you earlier. Let's look at real GDP first. What did real GDP do? Look at the maximum deviation from 0. Is that above or below 0? Well, it's above 0. How do we know? Well, it's maximum deviation right about here at about 2%, or I guess 2 percentage points. It increases by about 2 percentage points above 0 in response to a total factor productivity shock. Okay. What happens to prices? Well, maximum deviation there, right about here. Draw it over. We're in negative territory, a little less than 1.5 percentage points below 0. Cool. All right. Monetary base, we'll get to that. We'll get to the real wages in a second. Let's look at hours worked. Hours worked, what did they do? They increased. The maximum deviation is about 0.8 percentage points. Cool. All right. That's interesting. So output increased, prices fell, hours worked increased. Okay, so hours worked increased. But remember, hours worked can increase and wages could increase or decrease. So if we had a labor demand shock and hours worked were increasing, well, then real wages would increase too. So let's look at real wages, see what they do. The maximum deviation of real wages is about 10 months after the shock, and it's a little more than, 1.2 percentage points above 0. So real wages increased and hours worked increased. By looking at these 2 graphs right here, I can tell you this is a labor demand shock consistent with an aggregate supply shock because output increased, prices fell, aggregate demand increase. Firms get this technology shock, they get to make more stuff, output increases, supply increases. Because of that, firms need more workers. They're willing to pay workers more. So what do? Well, they need more workers, they need to hire more workers. The real wage increases so that they can pay workers more, right? So the workers' real wages will be increasing while the hours worked also increase. Cool. So just with these 4 variables right here, we're already pretty sure this is a total factor productivity shock. Now, can we be fairly confident that these are like significant responses? The answer is yes, because, well, this is above 0 at the maximum deviation. This is below 0 at the maximum deviation, right? And this upper Bayesian credibility band is below 0, so okay, we're good there. Hours worked, yep, above 0. Real wages above 0. Awesome. Okay, so remember, right, you had an increase in the LM curve at the same time. So if the LM curve increases, well, the money supply, the money base in this case, would be increasing, which we see. The money base increases, and the 10-year Treasury yield falls. Now, you're probably going, Jeremy, wait a minute, whoa. The 10-year Treasury yield is a nominal interest rate. Why aren't you using a real interest rate? Well, you can actually back out what the real interest rate is here. Just get the inflation rate and subtract that from the nominal interest rate. Boom. There you go. So, all this stuff right here, consistent with a total factor productivity shock. So the data tells us that the real business cycle model predicts a total factor productivity shock really, really well. So U.S. economic data is, when put into this type of a model and tested, confirms the predictions of a total factor productivity shock in the real business cycle model. And it also confirms it for the new Keynesian model. So overall, yeah, I'd say things are pretty good here. So we can at least check one off for both models on the total factor productivity shock. What about the labor supply shock? Again, either model. Remember, in the labor supply shock, the only difference is that wages fell in the labor supply shock, and in the total factor productivity shock, wages increased. All right, so that's the only way we could identify the difference between the two shocks. So what happens here? Well, first, let's look at the aggregate demand, aggregate supply thing. All right. Prices fall, output increases. It doesn't increase by a lot because, again, there's no productivity increase here. That's this A term isn't increasing. So the curve isn't shifting out. Oopsie. Because the source of the shock is coming from labor markets, not production. And it's a labor supply shock. Therefore, wages are going to fall, but the hours worked will be increasing. Total hours worked will increase, which gives us a new point on this production curve, over and up. Aggregate supply shifts out a little bit. Like I said, prices fall a little bit. Let's look at this. Real GDP, it increases. Again, how do we know it increases? Well, because 0 is right here, and this is above 0. So the maximum deviation is above 0 here. So real GDP increased. Prices. Well, the maximum deviation for prices is right about here. Yeah, prices fell too. That's cool. What about 0.12 percentage points below 0? All right. Hours worked. Well, hours worked increased. Again, not like by a whole lot here. All right. I believe. I'm going to go back and look. Yeah, hours worked increased, but not by as much as they did in response to a total factor productivity shock. The same can be said, actually, for prices and real GDP. Let's look at real GDP. 2 percentage point increase in real GDP in response to a total factor productivity shock. 0.4 percentage point increase in real GDP in response to a labor supply shock. Prices, what about 0.12 percentage points below 0? Here, more than a 1 percentage point below 0. So the responses so far are consistent with the labor supply shock, both in direction and magnitude, because the directional responses are the same, but the size, the amount of the responses. Remember, the real business cycle model predicted a less of an increase in output, thus a smaller reduction in prices in response to a labor supply shock compared to total factor productivity shock. So far, this is actually lining up pretty well. Here's the thing, though. Look at real wages. What are real wages doing? Your first thought's going to be, okay, well, they increased. And you wouldn't necessarily be like that out of line for thinking they increased. Because, well, it looks like they're increasing, right? They are increasing. But look at what's going on here. They're increasing after the initial drop. So after that initial reduction in the real wage rate, it eventually kind of increases, and then it'll sort of level off to something that is, well, At the end, it levels off to something that's about like 0.47 percentage points below zero. But the initial response, the initial shock, is the maximum deviation that we're seeing here of about 0.6 percentage points below zero. So real wages fell. Because again, you got to look at the numbers over here. Are they negative or positive? If they're negative, well, then it's a reduction. So real wages fell. Output increased, prices fall, hours worked increase, real wages fall. Money supply increases, but not really by very much. Therefore, can't really say for sure one thing or the other that's going on. But, if we're just going to look at the red, it's probably in line with the real business cycle model. 10-year Treasury yield. Okay, again, it fell because, look, negative 0.02, negative 0.04, negative 0.06. So the 10-year Treasury yield's falling as well. So in this case, the magnitude of the responses and the direction of the responses are in line with what the real business cycle model would have predicted, because the directions are similar to what the real business cycle model predicted, but the quantities by which these guys moved are also in line with what the real business cycle model or even the new Keynesian model would have predicted. So far, so good. 2 out of 3. Cool. Monetary policy shock time. Now, with the new Keynesian model, you get real responses to a monetary policy shock. So money increases, the real interest rate falls. Prices and output increase, labor and wages increase. But the real business cycle model tells us something a little different, which is that output, wages, and hours worked would remain unchanged in response to a monetary policy shock. So in that case, the nominal interest rate would fall, but the real interest rate wouldn't. So the 10-year Treasury would still move, but it would be offset by price movements. So you'd kind of have to look at like the two impulse responses between 10-year Treasury and then the one for price and go, all right, is the price movement offsetting the 10-year Treasury movement? But let's just see. If things increase, but they don't significantly increase. So let's say if output increases, right, but those Bayesian credibility bands are on either side of zero, well, then that would probably be evidence more for the real business cycle model than it would the new Keynesian model. Now, if we look at what the new Keynesian model predicts, right, predicts an increase in prices, increase in output, hours worked, and real wages in the short run. And then in the long run, everything kind of returns back to where it was. So let's see what's going on here. Real GDP. Okay. Real GDP increases. Now, I've got real GDP and consumer prices fixed at zero on impact. So the impact still happens at t equals 0, but their responses are fixed at 0 because it's a surprise. The monetary policy shock is a surprise to the real productivity, the real, like the private sector of the economy. So it takes at least just a little bit for them to be able to respond. So on impact, real GDP and prices are at 0 here and here. But let's look at the maximum deviation. Well, the maximum deviation is a little more than 1.25 percentage points above 0 for real GDP. Significant because this lower band is above 0. Okay, so about 1.25 percentage points above 0. Prices, their maximum deviation is about 0.4 percentage points above 0. The money base, well, that increases. Increases by design here because, well, I wanted the money base to increase. 10-year Treasury yield. Now, again, you might think it's increasing. It looks like it's increasing if you look at it until you look at these numbers here. Negative 0.1, negative 0.2, negative 0.3, negative 0.4, negative 0.5. Okay, negative 0.5. Now this isn't in terms of percentage points. What is this? This is in terms of basis points. So this would be, 5 basis point reduction in the 10-year Treasury yield, I believe. It falls. Now, it increases after it falls a little bit, which actually is consistent with what we would be seeing here. The real interest rate falls, and then it increases a little bit. Here, now granted, this is the nominal interest rate, but it falls and it actually increases a little bit. So that is in line with what the New Keynesian models suggesting. Okay, so the 10-year Treasury yield falls significantly because this upper band is, below zero. Let's look at the real wage rate. Okay, well, this one's a little murky. Initially, it's about a little more than a 1 percentage point increase in the real wage rate upon impact. And at least for a little while, it is significantly above zero. So real wages increase. Let's look at hours worked. Okay, hours worked increased. Okay, and then they kind of trail off, go back towards zero, which would be suggested by monetary neutrality, the neoclassical synthesis that we learned about in the last lecture. But it does increase, and its maximum deviation is about 0.36 percentage points above zero. So the qualitative responses in all of these variables are consistent with what the New Keynesian model would be predicting. Now, it appears to do a better job at predicting the responses to a monetary policy shock than, say, the real business cycle model does. In the short run, monetary policy can have real economic effects. During the sample period, there's some debate over what the transmission mechanism of monetary policy was, though. It likely operated through the yield on treasury bonds, which pushed investors into private equity markets. The idea is if you're holding a lot of these long-term treasuries, you're getting, whatever the yield was on those bonds. If the central bank comes and buys up all of those treasuries, well, the yield on those will be falling. And you're going to go, okay, well, I can get a higher return if I go elsewhere, namely private equity markets. So you go into private equity markets, you buy stock, boom, that ends up driving real economic activity. So they were trying to target the yield on the 10-year Treasury, which is why the 10-year Treasury yield is argued to be the transmission or the variable via which this transmission mechanism operated. The title of that transmission mechanism is what's known as the portfolio rebalancing channel. The idea is you had a portfolio with a bunch of treasuries in it. The Fed buys up a lot of treasuries. The yield on that falls. You want a higher yield. You dump a lot of the treasuries that you have, and then you go and rebalance your portfolio by getting stocks in private equity markets instead. Now, the real business cycle model shows some accuracy in the long-run behavior, but real GDP doesn't level off towards zero as we would have expected. This could also be a feature of the sample data. We run from 2008 to 2023. We had, two regimes of unconventional monetary policy? There was the financial crisis, and then there was COVID. And some of the other variables, though, seem to line up with what the real business cycle model could or would predict. So maybe it's just the data, maybe it's the regime, maybe we're crossing regimes and there's weird correlations going on because we're looking at, different regimes of monetary policy. A lot of different possibilities here. So, just because this isn't suggesting monetary neutrality, because, it would otherwise go back towards zero, just because it's not necessarily suggesting monetary neutrality, again, this is only also for 60 months. So, if we go 70, 80 months, maybe it just totally drops. We don't know here. But it's not necessarily that the real business cycle model's failing. We also have to be very aware of the behavior of the data and what the data is giving us, what the data is telling us. So let's say we wanted to restrict the sample period to October 2008 up to February of 2020, which drops everything during COVID and then after, because COVID was an extremely special circumstance, probably needs its own separate attention. Might not have even been a good idea to let the two mix when we're looking at a monetary policy shock. So it's not always the best idea to include different monetary regimes in the same sample. Now, for those of you that have taken statistics and you're like, okay, well, I remember about this degrees of freedom thing, and you always want to have more data. We always want to have more data. More data is better than less data, right? More data is always better. However, the data has to be relevant. If the data is not relevant, there's no point in having it. And there's arguments over the relevancy of the data across different monetary policy regimes, because they can have different monetary policy targets, different goals, different effects. There was the change in the inflation targeting regime where they went from a 2% to an average inflation targeting regime of an average of 2%. So, like, different things like that could really be contaminating the sample period. So there's a lot of debate over what time frames we would want to be using. So maybe this would be, if we restrict the sample, maybe that's going to give us something a little bit closer to what the model says we should expect. And it kind of does a little bit. Not in like the best way possible, but the 10-year treasury yield drops and then kind of increases up towards zero eventually. Real wages increase and then go towards zero. Now, it says that they settle a little above zero, but, I mean, if you're looking at the Bayesian credibility bands, are on either side of zero, so at that point you can't really say anything. It's not a significant result. Hours worked, well, you see an increase in hours worked, but then they kind of trail towards zero. Prices increase and stay above zero, kind of level off above zero. So, again, you'd expect that, right, for the long-run response, because the price level would be higher than it was prior to the shock. Real GDP, it increases, and it starts trailing off towards zero a little bit. Now, again, you can't really make a whole lot of inference with the slopes here because there's certain corrections that we have to make with the credibility bands. But if we're going to be a little cavalier econometrically speaking, it looks like it's trailing a little bit closer towards zero than it was previously. And then also the credibility bands are rapidly approaching zero. And I guarantee you, if we went 70, 80 months in this horizon here, you would see we're at a point that we can no longer, credibly say if it's above or below zero because, well, the lower credibility band would be below zero. And again, if they're on either side of zero, you can't really say anything one way or the other. So my guess would be here, by restricting that sample period, we're probably getting something that's a little bit closer to what the real business cycle model would be predicting for us. Now, why would including the other one not necessarily give me those results? Well, the monetary policy regime is different. So it's like the narrative is a little different. It's not to say that the real business cycle model isn't still going to hold, but because there are differences within the data, trying to combine the two sample periods could be giving me some problems. Now, if I were to have included just COVID, you'd probably see something, again, in line with what the new Keynesian and real business cycle models predict. But with a lot of the wonky behavior in the data, especially, let's cut all the way back. Back. What's up? Boom, here we are. Okay. Real GDP. Look what it does in the first quarter of 2020. There's that gigantic drop, and then it increases dramatically and eventually kind of converges back to where it was and, goes back to its original long-run trend. Look at what prices did around the same time, a little after, I guess. They totally increased. Look what the money base did. That huge increase in the money base. So you get all these really bizarre, totally sharp movements on a lot of these variables that could really be screwing with the ability of these econometric models to do what they're, I guess, really supposed to be doing. So trying to go across these two sample periods, maybe not always the best possible idea. But overall, this really was a great way to test out the real business cycle and new Keynesian models. And again, overall, we can see in the short run, the new Keynesian model holds up pretty well. It shows the adjustment phases to total factor productivity and labor supply shocks that result from the nominal rigidities, and it explains the effects of a monetary policy shock in the short run really well. Real business cycle model also holds up pretty well because it shows the effects of total factor productivity and labor supply shocks, and both models seem to be supported in the long run behavior. The GDP response, it's a little different. Probably should have shown some more convergence towards zero. But like I said, that could be a feature of the data. And if we include different samples, which is probably the smart thing to do in the first place, at least for a monetary policy shock, you can see we get some slightly different behavior. So that wraps this up. I know this one ran a little long, but I'm sure you can tell this is kind of a passion of mine. This is actually what a lot of my dissertation research ended up looking like. So thank you for watching. And we'll be talking about the financial crisis of 2007 and 2008 in the next lecture, which will be coming, I guess, next week, since this is, the week of Thanksgiving. So thanks for watching, and there's more videos to come in the future.